Hey there, chemists. In this crash course, we're going to look at stoichiometry and just a little bit of the kinds of things you need to know for the AP exam. First of all, we're talking about quantities in chemical compounds, so you should be very comfortable with converting masses of things into moles of things. Remember, the moles of a substance, often abbreviated N, is just the mass of that substance divided by the molar mass, and we get molar masses from summing up elements' atomic masses from the periodic table. So know how to find elements on your periodic table, and you'll have no problem getting quick molar masses. It's possible you might need to convert things into particles or atoms, and for that, remember Avogadro's number is roughly 6 times 10 to the 23, anything per mole. So it could be atoms per mole of an element, or it could be molecules per mole of a compound. Is just a number. It's just a very, very large number, and it's how much is in 1 mole of anything. The percent composition is something that's very useful for identifying a compound. The percent is an element. It's the mass of the element divided by the mass of the compound times 100. So, for example, if I have the compound methane, my percent carbon and my percent hydrogen would be, considering 1 mole of methane, there's 12 grams of carbon per the 16 grams of 1 mole of methane, and you get 75% carbon. That must mean the rest is hydrogen, but you can prove it. 4 over 16 times 100 is indeed 25%. And more commonly, you turn these percentages into a formula. Normally, we're actually given percentages. You can get those from things like mass spec, and we have to turn those into an empirical formula. So I would take my percentages, turn those into grams, and then turn those into moles. So there is 1 mole of carbon per 12 grams, and there's 1 mole of hydrogen per 1 gram. So I have, in 100 grams of stuff, I have 25 grams of hydrogen, and then I have 6.25 grams of carbon. Sorry, not grams, those are mole values, aren't they? Those are mole values, because we're converting them into moles. So my formula would be C 6.25, H 25, and then you normalize. That means divide both by the smaller of the set, and you would get a 1:4 ratio. So it's possible you might have to turn a formula into a percentage or percentages into a formula, but they're essentially the same thing, just in different directions. Lastly, the thing we did a lot in the stoichiometry unit, and frankly since then, is look at mole-to-mole ratios for balanced reactions. For example, if I react nitrogen plus hydrogen, one reaction that's possible is the synthesis of ammonia. You would make 2 equivalents of ammonia for every 1 equivalent of nitrogen and 3 equivalents of hydrogen. And then that tells me my mole-to-mole ratio. This means that I have 3 moles of hydrogen per 2 moles of ammonia, or 1 mole of nitrogen per 3 moles of hydrogen, or whatever ratio I need given these coefficients in order to do some conversion from moles of one substance into moles of something else. So that's a very quick breakdown of the kinds of things you might see. Well, let's look at some practice questions, starting with some multiple choice. A sample contains 42 grams of a hydrocarbon. It's got 36 grams of carbon and 6 grams of H. What question can be answered using this procedure? Let's see. Well, the volume of the sample is not something we can answer. You would need the density in order to do that. Density equals, I don't know, so can't do that because density converts mass into volume. It should be able to answer what's the molar mass of the compound. However, not necessarily, because I don't actually know the molecular... I don't know the molar mass of the compound because I don't know the molecular formula. Mass spectrometry would be used to get the molar mass of the compound that weighs molecules. Chemical stability, you need some reaction information in order to do that. Need reaction info. to do that. So it must be the empirical formula, which is the lowest whole number ratio. It almost sounds like molar mass is the right answer, but that's not the right answer because I don't know any mass spectrum information from this. They didn't ask me to get the empirical formula, but you could certainly do it. There's 36 grams of carbon and 6 grams of hydrogen. So I have C 36 divided by 12, H 6 divided by 1. That's your moles of C and your moles of H. So that turns into C3, H, 6. And then my lowest whole number ratio, that just means it's 2 to 1. And that's what an empirical formula is. We don't know what the molecular formula is because we don't know the molar mass. If we were given that, we could turn this and see how many multiples it is. Okay, next one. A student has a mass of pure copper. What's useful in finding the number of atoms of that copper? Well, your mass of copper could be turned into moles of copper based on its molar mass. I get that from a periodic table. And then if I wanted atoms, there's Avogadro's number of atoms. I'm just thinking about what I would have to do if I actually take some mass of copper. Oh, it's 21, isn't it? If they tell me exactly what it is. And turn it into it. All I really need is the molar mass of copper. There we go. That's the first choice. Everything else doesn't make sense. A density would be able to turn my mass into a volume. The volume of copper might be able to get me the density of the copper. The ratio of the isotopes might help me get the different atomic abundances, but it wouldn't actually get me how heavy those coppers. If I know it's a 2 to 1 ratio of isotopes, I still need to know how heavy those isotopes are to get the molar mass of copper, which really should be the atomic mass of copper, but I think that's what they mean. Next, which 1 mole sample has the greatest mass? So to convert these moles into masses, you multiply by the molar mass of each compound. NO is 14 plus 16, that's 30 grams per mole. NO2 would be 46. It's just 1 nitrogen and 2 oxygens. N2O would be 44. And N2O5, that's got to be the biggest number. 2 times 14 plus 5 times 16. I don't even have to do this math, but just to prove it to you, you're multiplying by the biggest number. Biggest molar mass would have the greatest mass. Easy. Last one. A student obtains a mixture of the chlorides of 2 unknown metals. So the percent by mass of X and the percent by mass of Z is known, which would be helpful in getting the mole percent of each compound. Well, let's consider what mole percent just means. What does that even mean? The mole percent of, let's say, XCl in the mixture, that means I really need the moles of XCl and then the moles of the sum, ZCl, and then obviously times 100 to make it a percentage. So how could I get the moles of these samples when all I know is the percent by mass of each one? Well, the percent by mass is going to be related to the mole percent in each compound. So I kind of need to know the identity of the elements, X and Z, so I can get these mass percentages and turn them into moles. So we must need the molar masses of X and Cl. The number of isotopes would just tell me how I could get the weighted average atomic mass. The density of the sample could turn masses into volumes. And the percent by mass of chlorine in the mixture would not get me to any mole percentages. It would get me to different mass percentages. I need to know how heavy X and Cl are so I can get these mole values. Okay, let's take a look at a couple of free response and wrap this up. Firstly, calculate the mass of H2 needed to react with N2 to form 25 grams of N2H4. I need to write a reaction for this. So H2 plus N2 makes N2H4. We got to balance this, so I need a 2 in front of the H2. And they want to know what mass of H2 to form 25 grams of N2H4. So I'm going to set up a dimensional analysis and convert until I get to where I need to go. So there's 1 mole of N2H4 for 32 grams. That's just adding up 2 nitrogens and 4 hydrogens. And then there is a ratio of 2 hydrogens for every 1 N2H4. So there's 2 moles of H2 for every 1 mole of N2H4. But they want a mass, so I need to say that there's 2 grams of H2 for every mole of H2. And then I can simply plug those numbers in. So that gives me 25 times 4 divided by 32. You get 3 1/8. And I'll round to 2 sig figs because the 25 is 2 sig figs. So simple stoichiometry problem, just had to write the reaction and turn my given value into what unit they're asking for. Lastly, conceptual question. A chemist determines the mass of potassium in a known mass of a compound that's either potassium oxide or potassium peroxide. Can the chemist identify which compound it is? So we know the mass of K and the total mass of the compound. That means we could actually get the percent composition, and we could get what it should be for both of those compounds. So yes, the chemist can find the percent K in the compound, which is equal to the mass of K divided by the mass of the compound multiplied by 100, and compare with expected percent K in K2O and K2O2. That should be sufficient. They didn't ask us to calculate anything. We certainly could if we wanted to go further, if we had time. The K2O would be 2 times potassium, 2 times 39.1 over that same number, 2 times 39.1 plus the oxygen of 16, and then multiply by 100. So 39.1 doubled, divided by that same number plus another 16, and then I get 83%. So just to prove to yourself, if you want to practice this, K2O is 83% potassium, but K2O2 would be 71% potassium. And we would just literally calculate the mass of potassium given divided by the mass of the compound, the known mass, and just, is it closer to 83 or closer to 71? Okay, so that wraps up a couple of practice questions that relate to stoichiometry, mostly mole conversions and how to use percentages by mass. Thanks for watching.